Good morning, this is Schweitzer, and we're looking to do an answer key for atomic trends on a periodic table. I consider this to be a concept that shows up pretty much every year. I tend to be under the belief that atomic structure and periodicity of the periodic table is just a means to test students for atomic structure. All right, so first off, it says create a Bohr diagram of the sodium atom. Okay, so we're talking about modeling atoms here. Again, your goal would be to try these out and check the answers afterwards. All right, so Bohr diagram of a sodium atom. Again, they're never going to see a question like this on an AP test, but the content that you're using to create this is everywhere. So when I want to create a Bohr diagram, I want to have my nucleus in the center, and a sodium atom has 11 protons. And I'll make sure that I have, there we go. All right, so in this situation, you'll see here on my periodic table that the sodium atom has 11 protons. All right, so it also is in the third row. So that means it has 3 energy levels, and it has 1 valence electron. So with that, we can do a lot. All right. So draw it out. If you want to, you just put like say 11 protons, and then 1, 2, and 3. And how you draw these is up to you, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There you go. Now, if I were to say sodium ion, then I'm going to lose this outer electron. And that would be isoelectric with, if you go to your periodic table, we drop back from sodium to neon, and we have 2 energy levels. All right. Next one, create a Bohr diagram of the potassium atom. Okay, so potassium is just 1 energy level bigger. So put the nucleus in the center. 1, 2, 3, and 4. And it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Let's verify that it has 19 and does 19 protons. All right. Now it says, all right, I kind of answered this question already. The sodium ion. All right, that's just this guy minus this electron. And then it's isoelectric with the neon atom. Both of these would have 10 electrons. How does the size of the sodium atom and the potassium atom compare? Why the difference? All right, so well, again, whenever I'm looking at comparing atoms, the very first thing I look at is energy levels. And as I just mentioned, these are the rows of the periodic table. So, for example, the sodium atom and the sodium ion is smaller because it lost an entire energy level. So that's why I look at that first. How does the size compare? Well, obviously the potassium atom is bigger than the sodium ion, Na for sodium, because it has more energy levels. All right. Now, the next thing I look at, number 2, is going to be referencing it, Coulomb's law, which is and we really want to use Coulomb's law to answer this question. Force is equal to the charge of the nucleus times the charge of an individual electron divided by the distance squared. So the number of electrons, or the protons, are radiating out attractiveness in all directions. So what's the force of attraction of the nucleus? Not to they'll attract all of them, but again, to an individual electron. That's the attraction an individual electron experiences. So how does the size of okay, we did that one already, energy levels. The second thing I look at is number of protons. Another name for this is effective nuclear charge. Now, you don't have to necessarily have to say that, but sometimes it's nice to know what that means. How does the size of the sodium atom compare to the sodium ion? What's the difference? Okay, well, again, we already mentioned this one, is that looking at energy levels. Now, this guy has the same, first thing, do these have the same energy levels? The answer is no. This guy's sodium ion only has 2 energy levels. Sodium atom has 3. So the sodium ion, Na plus, is smaller than the Na atom. And why? Energy levels. Now again, you wouldn't just want to say energy levels. You want to say sodium atom has 2 energy levels because it lost outer valence electron. Therefore, it's smaller. On the periodic table, draw an arrow showing the trend just discussed. Okay. So we just know that as we go down the periodic table, we're getting bigger because we have more energy levels. All right. Now we're moving into number 2, which is the number of protons, and number 3, number of electrons. And I go in that order as far as discussed, how we deal with them. So, it says draw a Bohr diagram of beryllium and lithium atoms. Okay. So it says, so let's see what we already find these guys. Beryllium is located right here, lithium's there. So 4 and 3. They have 2 energy levels. This guy's got 2 valence, this guy's got 1. Alright, so do it right here. I'll do it over here. So beryllium has 4 valence electrons, 4 protons, 1 energy level, 2nd energy level, and 1, 2, 3, 4. And then the lithium has got 3 protons, 1, 2, and like so. The beryllium atom is smaller than the lithium atom. Using Coulomb's law, I'll explain this. Alright, so we want to use the fact that, okay, first thing we go to is energy levels. They are in the same number of energy levels as 2. And I wrote that wrong here. It's only going to have 1. All right, now we have a number of protons. Well, looks like lithium has less protons. So you can say that lithium is smaller than beryllium. I should say, hold on a second here. So beryllium has more protons. So beryllium is smaller than lithium. Why? Because of greater, okay, protons. You can't just say greater protons. Greater protons causes greater Coulombic attraction. Pulling electrons in. This is another definition for effective nuclear charge. So we always want to use, whenever we're doing 2 or 3 here, reference Coulomb's law every time. All right. Next. All right. Write out an electron configuration for beryllium and boron. So beryllium we just did. Beryllium 1s2, 2s2. Boron is going to be 1s2, 2s2, 2p1. The radius of boron increases slightly from beryllium, but then continues to get smaller than boron, and nitrogen is smaller yet. Okay, why is there a slight bump between beryllium and boron? So this is what they'll do lots of times. They'll give you information, ask you to kind of justify it. What they're saying here is that this guy, we just mentioned beryllium is smaller than lithium. Okay, more protons. All right, but then they say, oh, for some reason, boron got bigger, but then it gets smaller, smaller, and smaller. What might be causing this to occur? And if you look at the this case, the answer is the addition of a p orbital. Okay, that's it. For some reason, that addition of p orbital causes a slight bump in the size. That's all we really have. You'll note that here, only difference is we add this guy. But then again, as we continue to add more and more and more protons, then the effective nuclear charge gets larger and larger and larger, and of course we get smaller and smaller and smaller. So as it wants us, let's draw the trend on here because it'll probably ask to do that too. So as a general trend, we get smaller, we get bigger as we go to the left here. Less protons, less effective nuclear charge. This would be your biggest atoms right here. All right. Why does this row get smaller as we add protons? Again, increased effective nuclear charge. That's this guy here. Increased number of protons. In an energy level. I'm not going to go through and re-describe everything because we did this already. Number of protons will increase the Coulomb attraction to all the electrons, pulling them in tighter. Now, describe the term effective nuclear charge. All right, so when we go on our periodic table, okay, let's take a look at maybe this guy right here. Someone can say, okay, as you go down the rows, you should get smaller because there's more protons. And or someone will say you might get bigger because you're adding energy levels. So the term effective nuclear charge only works when we're comparing within a row of the periodic table. Because this is where essentially we have a nucleus and we have an energy level. How effectively is the nucleus able to attract to a given energy level? So if I add more protons, I'm not getting any farther away, so the rate at which my nucleus is more effective at grabbing onto these things is increasing. So I don't have to worry. And of course, there are more electrons between here, but those aren't increasing, and the side distance away really isn't changing a ton. So adding protons within a row is effective nuclear charge. I'm going to abbreviate that. It's not a normal abbreviation, effective nuclear charge. Okay. I would not abbreviate that normally. All right. So it's addition of additional protons in a given row. So for example, you wouldn't say that sodium is bigger than the sodium ion because of the effective nuclear charge. That just isn't true. It's bigger because of more energy levels. All right, we did number 9 already, showing the trend. According to the trends list, which might be the biggest atom, well, that'd be francium. It's in the bottom left-hand corner. All right. Draw a Bohr diagram of the oxide and aluminum ions. Okay, so we have oxide. Let's just find these things quicker here. Now, if you think of a couple things you might notice about this, this is the oxygen atom right here. Oxide means it's going to gain 2 electrons to become isoelectric with neon. And that's a pretty important idea to be able to explain why it gains 2 electrons, because it wants to have a full outer shell, thermodynamically more stable, not happier, no homogeneous characteristics. Now we have aluminum, has 3 valence electrons, so it's going to lose 3, also becoming isoelectric with neon. So these two atoms are going to have the same number of protons. So let's just do this quickly here. Oxygen has 8 protons and has 1, 2 energy levels and 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The aluminum atom has 13 protons. Still the same number of energy levels and same number of electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Which atom is bigger? Which atom is smaller? Okay. Like I said, we go from number of energy levels, number 1, number 2, number of protons, and then number 3, electrons. Okay, these guys are in the same energy level. You should note. After they've gained the lost electrons, they both have 2 full energy levels, just neon 2. A fairly stable configuration, might add. All right, so now we go to protons. Well, the aluminum has more protons, just pulling them in tighter according to Coulomb's law. So who has bigger? Aluminum smaller, oxygen's bigger. Less protons, less Coulomb attraction. Again, you can't just say less protons. Compare the two atoms of fluorine and fluoride. Okay, so let's do that right here. Fluorine, all right, just find them here. Now, fluorine we locate here, 9 protons, 9 electrons. Fluoride has 1 more electron. There you go. All right, so 9 protons. So fluorine is going to have 9 positives. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's fluorine. And fluoride is going to have 10 or 9 protons. 1, 2, and the whole thing is going to look just like these 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Compare the two atoms. Doesn't say how, but I would note that same number of protons. Okay. Same energy level, so these are the same. Number of electrons, okay. Fluoride is bigger than fluorine due to electron repulsion. And this also is Coulombic repulsion. Coulombic electron repulsion. In this case, more electrons. Electrons will push away from each other, causing to swell ever so slightly. And fluoride is therefore bigger. How many energy levels are composed in each of these atoms? Well, there's 2. How many protons? 9. Which atom has more electrons? Well, fluoride has more electrons. The fluoride atom is bigger than the fluorine atom. Use Coulomb's law to describe this. We already did that. Okay. So, investigating atomic radius. Here are our 3 deals. Okay. Make sure that here you write down electron repulsion. It's all that's required for that justification. We only do that when all the other ones are already being addressed, going in this direction. All right, next one. For the following atoms, use energy levels in Coulomb's law to predict and justify the following questions. Use the following symbols, size, for significant size differences. Okay, so fluorine, chlorine. First thing I do is I go to the periodic table and I find them. And they're not just picking random atoms. They're picking ones that are like in the same, just right above one another, or in the same row. So typically speaking. So we know that chlorine is bigger than fluoride, a lot bigger, because it has another energy level. So chlorine is much bigger, not just a little bit. Justify energy levels. Again, I'm going to abbreviate here because I don't want to just try to save time. All right, fluorine, argon. Let's try and find those ones. And find them on the periodic table. Fluorine, argon. Okay, once again, energy levels. All right, argon is much bigger than fluorine due to energy levels. All right, bromine, or bromine plus 2. All right, so in this case, bromine isn't normally going to form this charge, by the way. I don't know if I should change that or what, but in fact, let's change it right now to bromine. It typically would be, maybe I meant barium, I don't know. Let's go, but let's do this. Change it to a standard charge would be -1. All right, so bromine versus bromide. Bromide's got one more electron, so this guy is slightly bigger due to electron repulsion. Electron repulsion. And we have the same thing here, and it should be -1. Yes, it is a little bit bigger due to electron repulsion. All right. One more example here, I guess we could do would be, let's say, nitrogen versus oxygen. Which one is smaller? Which one's bigger? Let's find them on the periodic table. Okay, so they're in the same row. Oxygen has more protons, so there we go. Oxygen is smaller due to more protons, more Coulomb contraction. All right, I think that's it. Move to the next page. All right, application of atomic radius. It says here, atomic radius is utilized in chemistry, is mostly utilized in conjunction with Coulomb's law in the formation of an ionic bulk crystal. Okay, so this is where we use it. The most prominent factor affecting attraction is melting point. Cations and anions in an ionic crystal. The most prominent affecting, okay, so they're saying that whenever we want to look at the melting point of ionic compounds, we're using the Coulomb's law to sort of justify that. So force of attraction is equal to the charge of a positive, charge of a negative divided by d squared. Now this guy is the charge of the atoms. Let's say like calcium oxide. This is a +2, -2. You literally want to reference those charges with Coulomb's law. And the distance squared is the internuclear distance. And that's how I would like to see that described. Internuclear distance. Okay. All right, so it says here on the following model below, draw arrows showing attractive forces and arrows showing repulsive forces. So I'm going to just pick a different color here. Let's go with red for attractive forces. Okay. So the attractive force here is what's holding these together. Let me just draw a line here. So it's between the nucleus of one atom, so this, and the electrons of another atom. This is an attractive force. All right, and this guy here is an attractive force. All right, another attractive force would be this guy attracting to this guy's electrons. This guy attracting to, I don't know who those belong to, but this guy attracting to this guy's electrons. A little farther, but you can see right here it should actually be, let's just take that off there. All right. And let's just say here. Okay. Short distance, long distance. Okay. Now let's go with the repulsive forces. We'll pick blue for this guy. All right. This guy is going to repel here, and repel here. Like charges repel, maybe repel there, I don't know. All right. So in this case, for the atom to successfully bond, okay, my attractive forces, get off track a little bit, not much, attractive must be greater than my repulsive. Okay, so, or the thing literally would just push away from each other. All right. So in the below, all right, is an energy diagram, energy internuclear distance diagram. How does the diagram explain the question? Okay, so in this case, when the atoms are real far apart, they're obviously going to attract. And the lower you get, the bigger the attractive forces gets. And then the higher you go, the less attractive it, or less stable it is. So the lower you go, the more stable, lower energy, lower, more stable. So in super far away, essentially we have no attractive forces. And as we get closer, the attractive forces are outweighing the, let's say, the repulsive forces. And then you get even closer, and they get even more attractive, and then really close, get to a point where they're close enough where the attractive forces are at their maximum. And then if you get any closer, the repulsive forces start to pick up. And then eventually, too close, and then eventually, if you push them closer and closer, it gets supremely unstable. And this is a common chart that you'll see, and I can hook this lines up. I don't care if you draw them all together like that. Okay. So what we have here is right here. Okay. This point right here is an interesting point. At this point, we're teeter-tottering between having too much repulsive force being too close, too far away, the attractive forces are bigger. This is at this point a balance where the attractive forces equal the repulsive forces. And we would say this right here would be the bond length, right, I should say right here, bond length, and this right here would be the bond energy. So as a general rule, just so we remember, single bonds tend to be longer, and energy tends to be lower. So triple bonds would be shorter, and energy would be higher, so bigger. So if I were to show a bond that would be, let's say, a single bond, I want it to be longer and shorter, so I might draw the pinnacle right there, and it might look something like that. Okay. That's how I deal with it. All right. Ionization energy. This is the amount of energy needed to remove an electron. Remove an electron. Second ionization energy. Energy needed to remove second electron. When write a chemical reaction for the ionization of sodium, I would also point out always gets more, this energy, the second ionization energy is always larger than the first, just so you know. Sure, we'll discuss that. All right, so write the ionization reaction. So it'd be a sodium atom. All right, and we're going to remove an electron. Write sodium. All right, +1, and then here's the electron I removed. I would also point out to you that pulling an electron away from something means you're fighting against Coulomb's law. That requires an input of energy, and this would be an endothermic reaction. Sometimes they would call this energy E, ionization energy 1. The second ionization energy of sodium, all right, the first ionization energy of sodium is much smaller than the second ionization energy, based on the board diagram above. Why? All right, so we have sodium up there, but we have sodium. So sodium has how many energy levels? Well, sodium's got 3. So it's got 1, 2, 3 electrons. So we pulled this first one off, and that required this much energy. To pull the second one off, it would be located right here. And it's not just close, it's much, much larger. So the reason why is because that electron is in a closer energy level. Closer energy level. And you'd always want to reference Coulomb's law whenever possible. Therefore, we have increased Coulombic attraction. And it takes more energy to remove. All right, next one. All right, statement A. The barium atom has more protons than beryllium, so it should be harder to remove its electron. Okay, so this is a true statement until we get to right here, and therefore we want to say false. Okay, it should be easier to remove because the electrons are farther away. Therefore, reduced Coulombic attraction. All right, statement B. Barium atom is easier to remove the outer electron. The barium atom is easier to remove the outermost electron than beryllium due to electron being farther away. So we're comparing the outermost electron of barium and the outermost electron of beryllium. And the answer is true. Again, it's just farther away. So we always reference energy levels first. So whenever we're doing this, reminder, energy levels, number of protons, then electrons. All right, that's like right here. And we reference the particulars on that as well. Are these statements true or false? Okay, so that's referring back, I believe, to the statement A and statement B. All right, looks like that's all we got on this page. All right, so using your knowledge of atomic structure and Coulomb's law, indicate all the substances are below differ relative to ionization energy. So energy needed to remove an electron. Again, energy level, number of protons, and number of electrons. Okay. So sodium and potassium. All right. Find them on the periodic table. Sodium, potassium. Potassium is bigger. All right. So in this case, we're looking to remove the outermost electron. So we're not removing the same electron. Okay, this is one clarification point here. Okay. These are bigger atoms, so I'm just going to kind of roughly sketch them out. Sodium, potassium. Now potassium has more protons. You know, it's got is it 19? Sodium. So 11 and 19. Okay, so 19 versus 11. 1, 2, 3. 1, 2, 3, 4. So this guy's got this electron here, this electron here. And I'm saying that it's going to be harder to remove the sodium atom because it's closer to the nucleus. This one's easier to remove because it's farther away. But we're not actually referencing the same electron. This electron is actually located right here. That's the same electron. If we were trying to remove the identical electron, well then potassium would be more difficult to remove because at the same distance it's got larger protons. Same distance, smaller protons. The electron we're pulling away is one that's farther away. So that's why it's less. Energy levels, reduced Coulombic attraction. Sodium versus Na+. Okay, loss in energy level, it's smaller. Therefore, this one's more difficult to remove. Same number of protons, electrons closer that you're trying to remove. C. Okay, this is one that is commonly mistaken. But I want to think of it in terms of just Coulomb's law. We've got fluorine. Okay, now fluorine has 9 protons and 2 energy levels. Fluoride's got 10 electrons, same number of energy levels. Okay, so let's just kind of draw this out. 9 protons, 9 protons, 1, 2, 3, 1, 2, 3. So in this case, they have the same electrons, but because same number of protons, but because this guy, fluoride negative, has, right, so again, go down the line. Number of energy levels, same. Number of protons, same. Number of electrons, okay. This guy's got one more electron than this guy does. So electrons are repelling away from each other, causing this thing to swell ever so bigger, making the number of protons and the distance to the electron a little bit larger, making it a little easier to move. All right. So this guy, amount of energy level, ionization energy is actually bigger in this direction. Smaller atoms, same number of protons, harder to remove. Same number of protons, large electrons, easier to remove. And remember, every time we remove successive electrons, it gets harder and harder and harder. So it would be easier to remove an electron from F -2. So it would get harder, harder, and if it technically was F +1, even harder. So the ionization energy gets bigger, bigger, biggest. Right? The most common wrong way is, oh, fluoride's got a full shell, it's more stable. No. Think of it in terms of Coulomb's law. All right. The atom doesn't care that its energy level is full, per se. Coulomb's law doesn't care. All right, neon versus argon plus. Okay, let's find these guys. Neon is located right here. Argon and apparently lost an electron, so it's back here. Either way, it doesn't make a difference. I'm not sure why that plus is on there. It doesn't make sense for a practical question, but they're in different energy levels. So in this case, this guy is bigger because it's closer. They're due to Coulomb attraction. Fluoride versus neon. Okay, so 2 ions. Let's go to, now, these two are actually in the same energy level. Okay, so in this case, and I'm just going to take that off there. I like a little remover anyways from my original. So fluoride neon. Okay, again, fluoride's right here. All right, neon's right there. Same energy level. This guy's got more protons, so it should be more difficult to remove the electron. That's it. Coulomb's attraction, more protons, and another name for this is Coulomb attraction. All right. We can get to electron, I don't really care. All right. It's got more protons at a given distance, makes it more difficult to remove. All right. Statement: ionization energy of oxide is larger than ionization of oxygen, since oxide has a full energy shell, therefore more stable, making it more difficult to remove just for nullified. This is a big, fat, sad face. We don't want to think about this. All right, this is not true. The oxide ion is easier to remove electrons, lower ionization energy than oxygen. Why? Because the electrons are farther away, therefore reduced. Due to electron repulsion, these electrons are farther away, and therefore less energy required. All right, here's a very common scenario. Okay, common question. They might put it in a data table, whatever. So we have several successive removals of an electron. You'll notice that the first electron took X energy, second one took 10 times it, and the third one took 100 times that. Justify or nullify the following statements. The second ionization energy is larger due to having a larger effective nuclear charge. All right, this is false. Okay, this is the same atom, so atom X. All right, and I'm just removing electrons. And what's happening here is I have my first energy level and I have my second energy level. So we automatically, when we see this, we want to be thinking about this. It appears that after the second electron is removed, the energy has a significant jump. So that means this atom actually had 2 valence electrons. And I remove the first one requires this energy, X energy. The second one requires 10x. The third one requires 100x. And the reason why this is 100x is because it's pulling from an inner energy level. So why is it that this one is more difficult to remove? One, technically, false. All right, it is larger, true, but the reason is false. The effectiveness is the same because we have the same number of protons. The effective charge would have more protons on a given energy level. Same number of protons, so the same effectiveness. The reason being, how I would describe this is that it is closer. It's closer because it has less electron repulsion. So for Coulombic, so therefore increased Coulombic interaction. The third ionization energy is larger due to loss of an energy level. This is true. Interrelating properties relative to the periodic table has become common in recent tests. Here are a few examples. Chlorine is used in swimming pools. What might be another substance from the periodic table that could replace chlorine if needed? Well, what you want to do for something like this is simply go to the periodic table and say, okay, well, here's chlorine. Really, anything in this family could work. So bromine, iodine technically could work. In fact, if you were to smell bromine or iodine or these things, it would smell a lot like chlorine. It does a lot of the same things. All right, so maybe not, I mean, technically fluorine, chlorine, and bromine could work. Fluorine is more reactive. It gets less reactive as you go down. All right. Silicone is commonly used to make microprocessors. What other materials could possibly use to make these substances? All right, so let's go to our table. Silicon, carbon, and germanium are chemicals that could be used also to make microprocessors. Maybe carbon, silicon, germanium. And coming to the end here. That is the end. Thank you very much.